said, I do teach our oceanography class, and it's one of the most fun courses for me because everything is so tied together. And so we'll talk a lot about that. And so this talk was originally scheduled for Naples, Florida. So I sort of made it up about Florida, but a lot of these issues have implications well outside of Florida as well. So I really want to talk about the effects of climate change, most specifically on Florida. And so the question is there too much carbon for a carbonate state? And so I'll talk a little bit about carbon dioxide and the greenhouse effect. And then I'll talk about two of the major effects that go along with that. And those are sea level rise and ocean acidification. So, so the first thing I want to talk about is the composition of the atmosphere. So many of us know that the atmosphere is about 78% nitrogen and 21% oxygen. So that's the air that we breathe is mostly nitrogen, a little bit of oxygen mixed in. And then the rest of the atmosphere, if we think about it in terms of percentages, it's 78% nitrogen, 21% oxygen, and 1% argon is the next one down. And if you're handy at math, you'll notice that that's 100%, that those total to 100%. So the question becomes, what about CO2? What about all the other gases? And we hear so much about CO2. And it turns out that CO2 is round off error in terms of percentages. CO2 is currently about 0.04% of the atmosphere. It's a little above 400 parts per million. And so it's a very small percentage of the atmosphere, but it has a very outsized importance because CO2 is one of the major gases responsible for what's known as the greenhouse effect. And so the greenhouse effect is simply that you get light comes in from the sun and warms the earth. And as it does that, some amount of that gets re-radiated back out into space, but then let's see here. But then some of that then bounces back down, gets absorbed in the atmosphere and stays, and then gets re-radiated back down to the earth and keeps us warm. And so this is what's known as the greenhouse effect. And a lot of people, because we hear so much about the greenhouse effect, a lot of people think that the greenhouse effect is a bad thing. I want to convince you that the greenhouse effect is actually a really good thing. So without the greenhouse effect, this is a picture of the planet Mercury. And Mercury has no atmosphere, so it has no greenhouse effect. And so Mercury is very close to the sun, so the sun's rays are very warm on it. And so the daytime surface temperature on Mercury is about 430 degrees Celsius, really super hot. But then when Mercury rotates around and you get on the dark side of Mercury and it becomes night, because there's no atmosphere to hold in the sun, hold in that heat, it's about minus 180 degrees Celsius. So, that's what happens without an atmosphere. And so so the greenhouse effect really does help us out. And so what happens when that light comes in, and so this 100% of light coming in, a bunch of that light is just going to bounce back out as this visible radiation. And so when we look at a picture of the Earth, we're looking at that 30% of the incoming light that just bounces back out, okay? And so that's the piece that bounces back out and is not impacted at all by the greenhouse effect. But a lot of the light that hits the Earth gets absorbed. And so the whole Earth absorbs that heat And it becomes, just kind of like a cast iron skillet. Once you're done cooking with that cast iron skillet, you turn off the heat, and it still radiates heat out of it. So the Earth does that all the time, okay? And so that it re-radiates that radiation over here as infrared radiation, as heat. And then some amount of that gets absorbed by water vapor and CO2 in the atmosphere. And it's this right here that gets affected by increases in CO2. And so if we increase the amount of heat that gets absorbed here, then that's going to affect the amount of heat in the atmosphere that stays trapped in the atmosphere. And so, so going back to this figure, in a normal situation, the greenhouse effect is really helpful. And so it traps some of that atmosphere, or some of that heat near the Earth. But so the greenhouse effect stabilizes the temperatures on Earth. And so we don't have those hundreds of degrees Celsius temperature swings. And so that really makes life on Earth possible. And so the greenhouse effect, we like, it's a very good thing. But as with many things, too much of a good thing can be bad. And so, so what happens is if we have too much CO2 in the atmosphere, then the atmosphere holds too much of that heat, re-radiates that back down to Earth, and we end up with climate change and global warming. So, and so that's where we are now, because carbon dioxide concentrations in the atmosphere are increasing and have been increasing ever since the industrial age began. And so this is one of those things that, this is just, it's straight up data. We have really good records that, that carbon dioxide is increasing in the atmosphere. And so this, as I said, this talk was originally going to be done in March. And so in March, the levels of CO2 were 413.95 parts per million. And then today, a couple of days ago, I got an updated measurement, and so it was 416 parts per million. So it's actually gone up by 3 parts per million since March. And one of the cool things that you see in this record is you see the increasing trend. So you see the increase in CO2 over time, but you also see this up and down pattern. And so that's a seasonal change in the amount of CO2. And so what's going on there is, because the Northern Hemisphere has so much more land area than the Southern Hemisphere, during the Northern Hemisphere summer, that all the plants grow, the grass grows, the trees grow leaves, and all of that pulls CO2 out of the air. And so that makes the levels drop during the Northern Hemisphere summer. And then they go back up during the Northern Hemisphere winter. And then you get that seasonal change continuing over and over again. One of the interesting things, given our current situation, is that so between March and May of this year, the CO2 levels went up by 3 parts per million. I went back and looked at some historic data, and for each of the last 5 years, between March 6th and May 14th, the CO2 levels have increased by 4 parts per million each year. So, so our current COVID situation has knocked down that increase by about 25%, which is sort of an interesting thing. But the problem is that all of these levels are way higher than they have ever been in sort of recorded history. So if we look at this over a couple different time scales, we see how dramatically different our current CO2 levels are from historical levels. So, so this goes back to the 1700. So this is 1700 levels of CO2, about 275 parts per million, slow increase and then rapid increase beginning in 1950 with the beginning of the record in 1958. And so CO2 levels now at 400 parts per million are fully a third higher than they were pre-industrial age. And if we go farther back, we go 10,000 years ago back, then the levels were at that same sort of, essentially, these levels have been between about 260 and 280 for 10,000 years, which is essentially the time of human beings being on Earth. So human beings have never experienced CO2 levels this high, and that's a problem. So, so the fact of the matter is that CO2 levels, carbon dioxide is increasing in the atmosphere, and there's just no two ways about it. It's going up. And so this carbon dioxide in the atmosphere has two really major effects. The first thing is it increases the global temperature. And so along with that, that is going to, the global temperature is going to influence sea level rise, which is the one thing that I'm going to talk about. And then the other thing that CO2 levels, or that carbon dioxide does, is it increases the acidity of the ocean. And so that's the other problem that it's going to generate and that I'll be talking about. So first off, let's talk temperature. So over the past 150 years or so, global temperatures have increased almost 2 degrees Fahrenheit. And so if we look at the baseline of this time series, this is the average of these years. And so essentially the temperatures have been increasing pretty much as those CO2 levels have gone up. And if we look at this in another view, so this is global temperatures in degrees Fahrenheit or degrees Celsius, and going along with the carbon dioxide levels. So the black line is our temperature, the red line is carbon dioxide. And you see that as the CO2 levels go up, so do the global temperatures. So, so the temperatures really are increasing along with that. And for the oceans and for Florida, sorry, before I go there, there are people who suggest other possible explanations for this increase in temperature. Things like variations in solar output, variations in ozone, variations in volcanic activity, because volcanic ash can go up in the sky and change the amount of solar radiation coming down. And then man-made sulfates, which are essentially pollution, which reduces solar input. So all of these things, people have figured out the effects that they would have. And then when you add all of those together and you look at the predicted effects from greenhouse gases, the greenhouse gases are the only ones that result in this sort of big increase. And then when you add all of those factors together, all of these other possible explanations that people have come up with for the increases in temperature, then you get this mottled line. So this brown line, and if you follow that, it follows the pattern of the black line, which are the observations, really pretty well. And so, so essentially, the story is that the CO2 levels are increasing, and they are causing the temperature to increase. And that CO2 increase is man-made. There's just no two ways about it. So we have increased temperature. What's that going to do to the oceans and to the Earth? The first thing is it causes more extreme weather events. It causes hurricanes to be larger. Most specifically, it causes them to increase in strength more quickly. And that's one of the things that we've been observing over the past few years. And this is largely due to the fact that water vapor powers weather, okay? So when water evaporates, it it absorbs, that water vapor absorbs heat energy, and then it goes up into the atmosphere. And when that water vapor condenses it back into water, it releases that heat energy back into the air, and that's what powers wind. And so because the heat warms the air, warmer air holds more water, and then you can have more water can condense and release more heat energy in and create more wind. That's why the warmer water causes bigger storms. And so it has to do with, it's a phenomenon known as the latent heat of vaporization. And anyone who took my oceanography class knows just how crazy I go over that number. We talk about water having a high specific heat capacity, which is the amount of energy it takes to change the temperature by 1 degree, and it's 1 calorie per gram of water. Whoop-de-doo. The latent heat of vaporization is 540 calories per gram. So it's a much, much bigger number. And that's the energy that drives storms. One of the interesting things, we just had Tropical Storm Arthur off the coast of North Carolina. Generally, the hurricane season begins in June, but in each of the last 5 Mays, going back to 2014, in the last 6 Mays, we've had 5 tropical storms, essentially before the season officially began. So that's one of the oddities that's essentially due to the fact that the ocean is warmer, and so it's firing up hurricanes earlier in the season. Now, where this gets really, Florida's in the hurricane zone, so that's a problem. But where Florida really gets into problems is the melting of glaciers caused by these increased temperatures. Because melting of glaciers is going to add more water to the oceans, and that's going to cause sea level rise. So this is a look, I want to talk about sea levels for a while. And so this is a look at sea level over time, okay? And so this is sea level going back about 250,000 years. And so our current sea level is here. And 18,000 years ago, we were in an ice age. And at that time, the sea level was really low. And then there's another time up here, I'll show you that in a second. But so sea level varies is the point. And so I want to talk about what causes these big changes in sea level. So the first thing that can cause sea levels to change and sea levels to rise specifically is when there's more water in the ocean. And so that is essentially when the glaciers melt, you have more water in the ocean. During an ice age, you have many more glaciers on the land, and there's less water available for the oceans, and the sea level actually goes down. The other thing that can happen is what we call the thermal expansion of water. When water gets warmer, it heats up. And well, there we go. When water gets warmer, of course it heats up, but what it does is it gets less dense. And what that means is it actually expands. And so the same amount of water takes up more space. Now, this is a relatively small change on the order of 1/100th to 1,000th of its volume, which seems like a very small change until you multiply that 100th or 1,000th times the volume of the ocean, which all of a sudden that very small percentage becomes a very big number. So, so the thermal expansion of water can change that. And then the other thing that happens is that the ocean basin actually gets smaller. And that's because the glaciers, specifically the glaciers on Antarctica and the glaciers on Greenland, actually hold those continents down into the Earth's core. And as the glaciers move, as the glaciers melt, those continents actually pop up. and they float higher, and so the basin actually gets smaller, and so that's going to make the sea level rise as well. So let's talk about what that means. So 18,000 years ago, we were in an ice age. So there were glaciers. They didn't quite make it down to Springfield as far as I'm told. But north of us was covered by super thick glaciers. And the sea level was about 120 meters below what it is today. So 120 meters, about 400 feet lower than it is today. And so at that time, Florida was really big. And so, so you had a much bigger continental shelf out here. The Bahamian banks, the shallow water banks areas of the Bahamas were dry. This is actually when a lot of these islands got built up and got bigger. But you see Florida extends way out over here onto the west coast. And so this is what happens when sea level goes down this much. On the other hand, 125,000 years ago, CO2 levels were slightly higher, and the temperature was warmer, and we were in an interglacial, and in fact, the sea level was about 5 meters above where it is now. And so one of the things that we do when we go to San Salvador and the Bahamas program is we go to a fossil reef. And so this is a place that's now about 10 feet above the water, but it was a coral reef at the time because it was covered by this high sea level at that time. This is what Florida looked like then. So, so this is the situation with 5 meters of a sea level rise, which we're not going to experience anytime real soon, but this is, Florida would be in deep trouble. It would be much, much smaller. And so, and you see only the very tallest places on Grand Bahama are still dry. So sea level varies with the amount of water in the oceans. And as we're heating up, we're adding water to the oceans. And so we're adding, we're definitely gonna change life for people who live on the coast. So, so just to give you an idea, so this is 18,000 years ago at the height of the Ice Age. Sea level was down here about 400 feet lower. Most of that increase happened before about 8,000 years ago. And since then, the sea level has been relatively constant with only a small increase. But we can see big changes over the last, say, 100 years in the amount of ice in glaciers. So this is one aerial view of a glacier in Alaska. This is another one. This is the Muir Glacier, I believe. And so you can see this is 1913, 2012. And so this is the Muir Glacier in Alaska from 1941 to 2004. So there's a tremendous amount of ice that has been lost from these glaciers, and that has made a real difference in sea levels. And so, so just to, so sea level has gone up by about 6 to 8 inches over the past 30 years in Florida. And so we can currently observe some of these effects along the coast of Florida. So one of the things that we see is what people call fair weather flooding in the streets of Miami. And so these are pictures from the Miami Herald of essentially, this is not during a hurricane. This is an average Tuesday of when the tide was super, super high. Okay, so this is a phenomenon that's now called a king tide. Now, I've been teaching oceanography for about 20 years, and when I started, king tides weren't a thing. Nobody talked about king tides. And but we talk about them now because we notice these. And so basically the tides are caused by the gravitation of the sun and the moon. So the moon pulls a bulge of water toward itself, and you get a bulge of water, and that's your high tide. And then the sun also makes a bulge of water that's a slightly smaller one. But so when the moon is full or new moon, we call those spring tides, and you get bigger tides. So the high tides are higher and the low tides are lower. So you have, we describe them as higher amplitude tides. So essentially you just get bigger tides because the sun tide and the moon tide add together. But the tides also get bigger when the moon is closer to the earth. And so because it's closer and gravity is affected by distance, you actually get bigger tides when those when the moon is closer to the earth. And so we've lately heard about supermoons, which is when you have a full moon when the moon is at perigee and it appears much bigger. It's interesting, the moon varies in distance by almost 20%. And so that makes a huge difference in the gravitational force on the water. And so it makes a really big difference. But so when you get a supermoon at a full moon, so you get the moon is close to the earth and it's a spring tide, you get a really big tide, and we now call these king tides. And the reason, these have always been there, but the reason we notice them now is that the base sea level is now high enough that when you add the high tides of these king tides, now you're getting this flooding. And so you didn't used to have that flooding because the sea level was low enough that the tide just came up higher on the shore. It wasn't a big deal. But now when you add the 6 or 8 inches or a foot of sea level rise, and then you add these tides on top of that, now we notice them. And so these, as I said, these tides have always been around, but now we notice them because they're based on it's building these king tides on top of that the already increased sea level. So so in Miami Beach, this is a problem. We're talking about a ½ a meter, 15.6 inches from 2016 to 2050. So that's ½ a meter of seawater. It's 1.5 feet or a little over a foot. And that's going to make a big difference. This talk was originally scheduled for Naples. So just to give a shout out to our friends down in Naples, we're talking about a 17-inch difference there is predicted by 2050. And so, so this could be a little problematic. And so, so let's give a couple concrete examples of the effect that this sea level rise might have on Florida. So I have to give a shout out here to a friend and colleague named Andrew Thaler, who came up with a program called Drown Your Town, which allows you to use Google Earth and do some overlays to figure out how much of your town would get covered up with a particular amount of sea level rise. So this is Naples, Florida, lovely place. And so all of the areas in blue would be covered by the ocean if Naples experienced a 1 meter sea level rise. So so the first meter probably isn't going to mess a whole lot of people up, but some people are going to be unhappy. But and so that's probably, we may be looking at that by 2100. But the second meter of sea level rise is when Naples gets in deep trouble. So so all of these areas that are covered in blue would be completely covered by the ocean at low tide, and this is at low tide, would be completely covered by the ocean with a 2 meter sea level rise. So, so much of South Florida is really low elevation. And so so Florida is really pretty, pretty subject to this, or pretty vulnerable to sea level rise. And so for those of you who are fans of the Florida Keys, this is just a satellite photo of the Florida Keys. And the Florida Keys are very low-lying islands. And so if the Florida Keys experienced 1 meter of sea level rise, pretty much only the very tops of the highest islands would be sticking out. So, so for those of you who are friends of the Florida Keys, we want to avoid sea level rise as much as we can. So one other thing about Florida that makes it different from many other places and makes it especially vulnerable is the fact that Florida is made primarily of, at least the southern part of the peninsula, is the bedrock is carbonate, is limestone. And limestone is very porous to water. And so as the sea level rises, the salt water actually comes in from the ocean and rises underneath that, the land. And so, so as that seawater comes in from the ocean, it just percolates right into that rock, and it lifts up the freshwater wells, the freshwater floats above it. But if your well pump is sticking down at a particular height and that sea level comes up, then that can actually, you can start pumping up seawater instead of freshwater. So, so that can flood freshwater wells, or that water can just rise up underneath seawalls. So this is from a website called sealevelrise.org, and just demonstrates that. So in a typical place like in North Carolina, where where the Duke Marine Lab is, the underlaying rock is granite, and it's a little bit porous, but it's essentially solid. And so if you build a seawall there, or if you've got the coast there, the saltwater intrusion is going to get stopped. But in Florida, that seawater is just going to come right underneath that seawall. It's going to percolate right through that rock and come right back up. And so that's definitely going to, has the potential to cause some issues. So Florida really is pretty vulnerable to sea level rise. And that's one of the, one of the inexorable complications. The word is leaving me. That's all right. One of the things that's going to come with increased temperature and with the increased sea level rises, or increased CO2 levels. So that's sea level rise, big problem caused by increases in CO2 in the atmosphere. So the next issue that I want to talk about, though, is actually a totally separate issue, but it is also related to excess CO2 in the atmosphere. And this is the process called ocean acidification. And so the increasing CO2 in the atmosphere, and I hope that I've convinced you that the CO2 is increasing in the atmosphere, is also going to come into the ocean. And when that CO2 comes into the ocean, it actually makes the ocean more acidic. And that's a problem. So what happens is the carbon dioxide combines with water, and it combines to form H2CO3, which is what we call carbonic acid. And so this is in all your soft drinks. When you put all that CO2 into the water to carbonate it, you make a lot of carbonic acid. In the ocean, that carbonic acid will turn into bicarbonate here, and then it'll throw off these hydrogen ions, and that's what's actually making it more acidic, is the excess of hydrogen ions. And the bicarbonate can break down to carbonate, to this other ion over here. And in the right conditions, carbonate can combine with calcium to form calcium carbonate here. And so calcium carbonate is incredibly important in a lot of different ways. Calcium carbonate is what makes up the shells of snails and clams and other mollusks. It's what makes crab shells hard. It does all of those things biologically, but then it's also what limestone is made of. So limestone is calcium carbonate. And so, and Florida is made of limestone, so Florida is made of calcium carbonate. Okay, so here is, it's time for our little audience participation game. So, so what I'd like you to do, if you've got this, and I will, I'll demonstrate this here. And so let me flip this over here. And I need to switch this. And so, come on, let go, share, come on. There we go. And I'd like to share my iPhone. Okay, so, so what I have here, yes. So what I've got here is, these are 2 glasses of water. I've got one, and these have pH indicator in them. And so at home, if you want to test your pH now, you can test your pH, dip it in your glass of water, and sort of set it aside and see what its pH is. So in here, I've got a universal pH indicator, and greens and blues are more basic, and yellows and red are more acidic. And so my breath has carbon dioxide in it. And so I'm going to blow bubbles into this one, and you should see the color change to indicate it's getting more acidic. So you guys can be blowing in your own also. You can see it getting to get slightly more yellow. All right, so I could keep going, but you can already see that there is a change from the greenish on this one to the yellowish over here. And that represents a pH change of about a half a pH unit. And just to bring this home, so what happens there is, so this is more acidic. And so when that water gets more acidic, it can dissolve calcium carbonate. And I'm going to simulate that by adding some baking soda back into this water. And so you can see that changing back to green or past green all the way to the blue. And so what happens is when the water gets acidic, the chemistry changes such that it dissolves that calcium carbonate to restore the pH to its proper level. And it's a purely chemical reaction. There's nothing that, there's no biology or no thought that happens there. But so that happens. And so let me switch back over here. All right, so so did anybody, was anybody else able to see that in their own? You can throw that in the chat if you want, just to see if anyone was able to change the pH of their water. Let me see here. Yeah, see, I can't see the chat. See, there we go. All right. Yes, all right, great. Excellent. Glad we got people got to see that change. So cool. So excellent. So here we go. All right, so what are the effects of ocean acidification? So as this seawater gets more acid, it's going to dissolve the shells of mollusks, of snails. It's going to make it harder for crabs to make hard shells. So this is a snail exposed to normal seawater. And then over time, as the water gets more acidic, it actually just falls apart. And so this is what's going to happen to some of the small planktonic snails that live in the oceans, is their shells are just not going to be able to stay intact anymore. The ocean acidification also slows the deposition of coral reef skeletons. So corals make a calcium carbonate skeleton. And so if you are in an acidified environment, it makes it much more difficult for them to lay down that skeleton. It's going to slow the growth of coral reefs. And so that will, that will just make it harder for corals to survive. Acidification can also exacerbate coral bleaching. So, so coral bleaching, coral have symbiotic algae called zooxanthellae, and the zooxanthellae give it its brown color. If you have a warm event or an acid event, the zooxanthellae can leave the coral, and it exposes, the tissue is still there initially, but you see right through the tissue because it's clear without the zooxanthellae, and you see the white skeleton. So that's what we call coral bleaching. If that stays bleached long enough, it can cause the coral to die, and then it just gets covered up with algae. So, so an acidified ocean is really bad for coral reefs. It can also increase the erosion of limestone coasts simply by that chemical dissolution. So, so that's not a good thing for Florida, which, as I said, is essentially made of limestone, and especially not for the Florida Keys, which is definitely made of limestone and is actually in a constant balance of new sand being formed by some really cool chemical processes and some dissolution. So, and then lastly, the acidification can decrease the phytoplankton productivity. And so this makes it harder for phytoplankton to grow. And since phytoplankton are the base of the food chain, that has bad effects that essentially go all the way up through the food chain. So, so these are all problems due to ocean acidification. And ocean acidification is just something that you don't hear about as much as you do about the other effects in terms of sea level rise and global warming. But so I just wanted to make sure that people heard about that. So overall, the question of climate change and Florida. So Florida is almost a uniquely vulnerable place to climate change. It's in the path of hurricanes, and so those hurricanes are going to be increasing in frequency. They're going to be increasing in strength as the atmosphere and the ocean warm to power those storms. Because it's low of elevation for much of the state, especially south of Lake Okeechobee, it's very vulnerable to sea level rise. And its carbonate geology is vulnerable to increased erosion and also the percolation of the seawater. So currently we really do have too much carbon for this carbonate state. Well, what are some solutions? How can we do this? So the first thing is we need to support science-based policies that can help us to reduce carbon dioxide emissions. And we need to do this globally, but we can start locally and at least in the US. Things like solar energy, wind energy, hydro energy are becoming much more cost competitive and can really make a difference in the amount of carbon dioxide that we emit as a society. We can personally drive less, we can carpool, we can do all sorts of things like that. We can support green energy. And then one of the other things that I want to talk about is that if we can change the market and follow past successes, then we can really unleash the power of human ingenuity to come up and solve this problem. There are two environmental issues that we have really solved just by market-based solutions. And I want to just call your attention to these because these are successes, and people made a lot of money off of these and of solving these problems. And so if we can just do something to change the market and put the incentives right, then maybe we can do the same with carbon dioxide. So sulfur dioxide emissions and acid rain. Acid rain used to be a huge problem in the Northeast, due largely to coal burning power plants in the Midwest. In the early 1990s, the EPA put in some regulations on sulfur dioxide emissions, and the power companies said, "Oh no, it's going to be terrible. We're going to die." And they said, we're not going to tell you how to do it. We're just going to say you have to do it. And they solved this problem in about 2 years at about 10% the cost that they were whining that it was going to cost, because some smart engineer came up with a effective scrubber, did it cheaply, easily, and you just don't even hear about acid rain anymore because it's not a problem. And that was a market-based solution. The other thing is ozone depletion. It actually drives me a little bit crazy because we have solved this problem of ozone depletion. In 1992, we passed the Montreal Protocol that eliminated chlorofluorocarbons. These are chemicals that were destroying the ozone layer and causing an ozone hole. And that was largely an ozone hole over Antarctica, but so we banned those chemicals, we phased them out, we're using different things now, and so the ozone hole has been, chlorofluorocarbon levels in the atmosphere have been decreasing, and the ozone hole has been getting less intense. And the ozone layer is essentially rebuilding itself because we are no longer actively breaking it. And so we can solve these problems. We just have to try, and we just have to make it pay for the right people to solve them, to solve the issue. What makes me crazy about ozone depletion is that we've solved the problem so thoroughly that my oceanography textbook that I use has actually deleted the section on ozone depletion instead of touting it as a problem that we successfully solved. So, so there really are some solutions to this problem out there. I think we can do it. I'm an optimist, but so we really can. I think that as a society we can solve this. So with that, I would be happy to pause and and to take any questions you have about this.
Awesome. Thank you so much, Jim. That was so interesting. Okay. Lots of big facts to digest now. There are a few questions over here in the chat. I can go ahead and unmute as well.
Okay. Stop the share. All right, cool. So, all right. Yeah, so the first question Ryan asks about any definitive information or studies about the impact of the lockdown. I just saw a thing today in today's post that said emissions fell by about a quarter over the past month, and so that's a big deal. And then, as I said, going back, the change in CO2 between March and May this year was about 3 parts per million. In previous years, it's been about 4 parts per million during that time period. So, which tracks with about that that time period, or that 25% reduction. So, so that's that. And Chip, I'd be happy to share my PowerPoint, so I'll do that. And cool. Yep. Southern end of the glaciers. Yeah, so they kind of got right down to us. How deep is the limestone layer? Pretty much the limestone goes all the way down. And so people in the drilling in the Bahamas have drilled 2 miles deep, and it's still limestone. There is no bedrock underneath it, and the process of that limestone formation is totally cool. Essentially, it forms actually by precipitation from seawater. You get super cold water in the deep part of the ocean, comes up onto shallow water, like comes up onto the banks of the Bahamas, and heats up super fast. And that change in temperature is so fast that the water can no longer hold the CO2, and the fastest way to get it out chemically is for it to precipitate. And so it actually goes from all that bicarbonate and stuff in the water precipitates as calcium carbonate, and you get these little round sand grains that get made called oolites. And it happens on every flood tide in the Bahamas and in the Keys, where you have that deep water coming up into shallow and heating up. Now, if the pH decreases, if it gets more acidic, then the conditions for that precipitation won't happen, and that gets a little tricky. But yeah, the limestone layer is super, super deep. Cool. Excellent. Glad the demo was cool.
How the magnetic changes factor in. There's been some speculation as to magnetic poles shifting or that side of things, how that factors into things.
So the magnetic pole is moving. I haven't heard of any ways that that's interacting with climate change, and I mean, it's certainly not going to affect the CO2 levels. And the wind patterns and things are affected more by solar heating and the Coriolis effect than by anything magnetic. So I don't anticipate. I don't know of mechanism by which that would change it, but I don't know for sure. But I can't think of a mechanism by which it would. But yeah, the magnetic poles do reverse every so often, and I don't really want to be alive during one of those switches because from what I understand, the magnetic field collapses before it reorients itself. And without the magnetic field, we would be bombarded by the solar radiation. So it would be decidedly unpleasant. So
I just didn't know if that also factored in with tide shifts and that kind of stuff too.
Not that I know of. Yeah. Cool. Yeah. So the question from Knox about the global response and questions about nuclear and other things. So yes, it requires a global response. The U.S. is responsible for a large amount of the CO2 emissions, and so I think we can be a part of the solution. Right now, the market, even with what subsidies are there for solar and wind, the amount of the subsidies for fossil fuels dwarf those, like almost order of magnitude. And they're so built into the economy that we don't even know that they're there. And they're so hardwired that it'll be difficult to get them out. But if we could get our thumb off the scale that's focusing it so much on fossil fuels, I think that there would be financial incentive that would drive this in the other direction. And so I think, government mandates are difficult and raise hackles, but if someone can make money off of it, and so if you just change the incentives just a little bit, then that's how you make it work. Is you tell someone, if you can fix this, you'll get rich. Then 100 people will try to get rich, and one of them might get it right. And if they do, more power to them. They should be rich if they solve this problem. But that's and a bunch of people can get rich solving it. And so personally, nuclear, I think responsible nuclear energy is a useful thing because of the low carbon footprint, but it has, because of the energy it takes to make the plant, that when you look at it doesn't have any daily carbon footprint, but its overall footprint is a little uglier than the initial sort of snapshot. The actual reaction on a day-to-day basis doesn't make any carbon, but building the plants and breaking them down and all the mining of the uranium and stuff adds to the carbon footprint. So it's not quite that simple, but there's certainly no reason to shut down existing nuclear plants. Cool. What resource could we use to refute any argument that it's a Chinese hoax? I mean, the degree to which the data on CO2 are just the data it's irrefutable. And you show them that graph, and you show them that graph over historical time, and and it's just there's no reasonable argument that CO2 levels are not increasing. And anyone who tries to make that argument is, I don't know how to say it other than there's no reasonable argument against the fact that CO2 levels are increasing. And so if they don't believe the data, then there's nothing you can do to convince them. And it's the physics of it. And if there's just show them the graph, and I don't, if they're subject to reason, then this is what you do. You show them the data, and so yeah. 1880s, smoky skies, carbon increase started in 1950. So the Clean Air Act definitely, the Clean Air Act mostly cleaned smog out of the skies. It didn't change CO2 as much. In fact, one of the current court challenges is whether CO2 can be regulated under the Clean Air Act. And so, so that's one of the questions and one of the current issues. And the reason that I think it's likely that the increase probably started before the 1950s, although the 1950s was a great expansion of the economy, and so therefore probably expanded our use of fossil fuels. Before that change in the graph is also a change in measurements. So prior to 1958, those measurements come from ice cores. And so they don't have the temporal resolution that the rest of that graph does. And those are actual measurements of CO2 from the atmosphere and taken on a daily basis. And so the figure that I was showing was plotting monthly averages, but the measurements are taken daily. And so, so I think that the increase was probably going on before then, but we just see it really clearly starting then because that's when that particular record starts. Question about Doug and the Great Lakes. So the Great Lakes, will the Great Lakes expand? Will thermal expansion of water affect the Great Lakes? For that one, they are more affected by the amount of rain. And so they get affected by long-term cycles of drought and rainfall. Currently, the Great Lakes are about at their highest levels ever, from what I hear, and I do most of my work, well, I do all of my work in the ocean, and I'm less connected to the lakes, but I've been seeing a few notices about that the Great Lakes are especially high right now. And that's due to the heavy rains that we've had over the past couple of years, more so than thermal expansion. But it is possible. And also the volume of the Great Lakes is enough smaller that that the multipliers aren't as big. So 1% of the Great Lakes is a lot smaller than 1% of the ocean. So cool. Jess points out a really great, yeah, so these are some really good ideas about refuting the idea that it's a hoax, skeptical science on Facebook, and relating personal stories. That's great also. And yeah. So in terms of, to answer Elizabeth's questions about Florida, I mean, I think I don't know the best way to do it. I think that the majority of people in Florida are, would argue that they want to preserve the beaches and preserve the state, because the state's economy depends on tourism. And if Miami Beach is flooded, then the hotels are flooded and there's nowhere for the tourists to go. And so in terms of Florida, it might be best to make the economic argument and put it in terms of dollars and cents, and that it's going to threaten their livelihoods. But you know, there are, and I'm a teacher. I'm not a science educator, and I mean, in terms of the public, and there is a lot of literature out there about if you correct people, it just they just dig in harder. And I don't know the best techniques to fight those things. There are people who know the answers to those questions, and I would suggest you look for resources for that. But I don't know. Yeah. So how long till 2 meters up? 2 meters up in current trends is probably not till 2150 or 2200. The issue is that even when you go, even when you add a foot, so a third of a meter, when you add the tides on top of that, or you get a hurricane come in and you have a storm surge, that just makes those much more devastating. And so even if your house isn't flooded on a normal day, it might be flooded on a spring tide day. And that happens every 2 weeks. So so that's not the best way to be. So so George asks about this current reduction due to COVID. And so there are a couple ways to look at it. One of the things that I saw today talked about this 25% decrease in emissions over the past 3 or so months, but pointed out that that was a 25% reduction with an economy that shut down. And to really reduce CO2 levels, we need to maintain this sort of 25% reduction and even reduce farther. And so it's awesome because that we can see the effect is a nice thing. But the fact that even with shutting down the economy, we only got 25% down is a little bit, tells us how big of a challenge we're facing. But I think if there are promising ways to get more energy that don't involve fossil fuels. And so I think it's a possibility. Yeah, and Chip makes a good point to hear people's point of view and not to yell. And I mean, it is the data are powerful, and so listen to them, hear them out, and show the data. And it's I didn't show some of the other time periods, but there are on the Scripps site where I got that data. They have that data over longer time periods, and so there's one that goes back several 100,000 years, and so essentially we have never. I mean, one problem is that we're not in equilibrium at these CO2 levels. CO2 levels have never been this high certainly not in the times of human beings, not in this alignment of the continents. So in tens of millions of years, CO2 levels have not been in this high. And the problem is that we're not in equilibrium yet. And equilibrium at these CO2 levels, I don't know how much of stuff is underwater or how many glaciers there are. And so, there's a degree to which we need to do some geoengineering to reduce the CO2 levels, not simply stop pumping it out, but we need to get some of it out. Because but it's going to take a while to get to equilibrium. So, I mean, we're still, one of the interesting things that I talk about in terms of equilibrium, the coast of North Carolina and some of the East Coast, someone's from the Chesapeake Bay in Norfolk. Norfolk is having a big problem right now because Norfolk, the land is sinking. And the reason the Norfolk land is sinking right now, it's still recovering from the Ice Age. So when the Ice Ages were here, you had glaciers. Let me get this. So the glaciers were on the center of the continent, and so the glaciers were pushing down on the center of the continent. So the coast was sort of pushed up like a seesaw, and the glaciers melted, and so the land sank back down. So Norfolk is sinking down because the other end of the seesaw is lighter now, but Norfolk is still sinking, making up for the glaciers going away. And so Norfolk is in a particularly bad place where not only is the sea level rising on an objective basis, but the land is also sinking because it's still catching up from the glaciers. And so Norfolk is another place that's in particular trouble with this. And they've got some really big tidal gates that they actually close, like down by the Wisconsin, the battleship that's there. They have some tidal gates they actually close so those super high tides don't come up into the streets. So, what are infrastructure changes Florida could make? I don't know. Yeah. To slow or change both ocean acidification and ocean levels, I mean, I don't know. The problem with the sea level rise is that because the water can percolate up through the bedrock itself, through the limestone, it makes it hard. New Orleans is closer to, at least I think it is, and I'm not a geologist, so I get out of my depth pretty quickly. New Orleans can pump water out and not have it come right back through the rock. Florida can't. So like, I mean, if you put a sump on a Miami street and you pump the water out, it essentially comes right back up. And so Miami's a little tougher to deal with that technologically. That makes that tougher. Or infrastructure-wise, that does make it a little tougher. So, yeah, cool. Yeah, and other places are raising streets. So I know that Miami and someone points out that Miami and Fort Lauderdale are raising streets, which is really expensive. I saw one of the stories I looked at in the Miami Herald said it described it as something like $2 million a mile to increase a street, the height of a street by about 6 feet. And we moved, we moved a lighthouse. We moved the Cape Hatteras Lighthouse 20 years ago to deal with this erosion. And I mean, that was more of an erosion issue than a sea level rise issue. So, yeah. Yeah, severe weather is increasing, and that's problematic. And that's, yeah. It is, severe weather is increasing, and it's going to keep increasing in the near term because as the atmosphere has more heat, everything happens faster, and so you get more wind, you get more rain, you get more water, and so I mean, it's like, well, it was 30 degrees a week ago here in Springfield. And so global warming isn't always warming, it's climate change. And so we get more extreme events. And what happened to cause this cold outburst was a bunch of the air that circulates around the poles, what's known, you've heard about, called the polar vortex, actually got displaced by some of that excess wind and dumped down here. And so that's why, you know, all my friends on Long Island were talking about snow, and we had frost. You know, we planted new plants in our garden. I had to pull the pots into the garage, and so they didn't freeze. So all of these extreme weather events are going to happen more frequently with this higher levels of CO2 in the atmosphere. So.
Hey, Jim, we're here at 4:45 now, so we can, if you want to stay on and continue to ask questions and everybody wants to keep chatting, we can definitely do that. But I just wanted to let you know. And also, I wanted to let everyone know that we've recorded the session, so it's going to be online on our virtual ways to engage page. I'll email everyone that link here after we get the recorded session and everything together. So. But yeah, that was pretty much all for me. I also wanted to see if we could take a quick picture and maybe we could all throw up our W and I'll do a screen capture. All right. Take her up. I love this. I think this is the greatest thing. Okay, let's see if I can do my W off screen. All right. I'm going to get a couple more, so hold it. Get everybody in here. Oh, I love this. This is the best. One more. Great. Thank you, guys. Thank you. And yeah, I'll leave that up to you, Jim, totally. I know that.
If you guys want to ask a few more questions, I'm happy to take a few more. And you know, it's possible to get out of my depth, but I'll do my best.
Hey, Rebecca?
Yeah.
Is different subject, but is the Toledo event on June 6th still on?
So I don't think it is. It's actually,
Okay.
I know it's not, but they're looking to reschedule it. Matt Peck we had been in conversations earlier this week, and he's looking and hoping for maybe in August, but it's kind of all so fluid right now that we're just kind of
With
trying
the whole COVID.
Yeah.
Hey, Dr. Welch, I jammed my keyboard so I can't type. Are these temperature increases cyclical? And what I'm referring to is Vikings used to come across to Newfoundland. And I've been told by the park rangers that they stopped doing it because they got tired of dodging icebergs. So
I mean, they're seasonally cyclical, but they're not
over time.
Not, I mean, there may be some cycles involved. There's certainly some cycles in ocean temperature that are sort of decadal cycles in temperature, but the global temperature changes that we're seeing far exceed the magnitude of any of those cyclical changes. You know, and what we're seeing is any of those cycles are building in towards an increasing trend. And so, so in the same way